So, good morning, everyone. Let us start. Yesterday, we did a lot of recap, so we have only a little bit new stuff which we need to recap today. The main new thing we did yesterday was this at the SRAM. So we talked about what different memory types we have, and you said already, well, we have some RAM, we have some ROM, we have some flip-flop stuff. And we started yesterday with this SRAM cell. So from a basic functionality concept-wise, what is the purpose of the different structures within such a cell? So let's start maybe with this transistors I have here named X, MX1, MX2. What's the purpose of this? Yes. Yes. So read and store the data. Yes, for this is the complete cell, actually somewhat. But in the storage process, why do I need them? What would happen if I would just remove them? Exactly. So it's just a switch that allows for access to the inner nodes. So if you would here directly connect, we always would be connected to bit line. We cannot attach multiple cells to the same bit line. If we completely disconnect, we cannot write the inner state. So these are actually the access transistors. They are not responsible for storing any data, they're just switches. And then we have this CMOS structures here and here. What is this inner structure here? Neglecting the MX transistors. So what kind of logic circuit do we have? Yes, there are two cross-coupled inverters where the output of the one is the input of the other one. And in this way, we have a stable, well, effectively we have two stable states, one metastable state. Metastable state means both are approximately VDD half. Any tiny variation would flip this into a stable state. And then we have the two stable states that we actually use for storage. That is 0, 1 and 1, 0. Is this, or did you ever hear about a stable metastable state? No. So I have to think that I can really do this. Good. Let's try like, if we have an inverter, and I need to think which way around to draw this. We have here the input voltage. So inverter structure in a CMOS technology built like this. So here at the input, we have the in, and here we have V out, which I immediately call, let's say, because that's exactly in this direction, we call VB. Okay? Then we have, this is actually our diagram that we want to draw. Now what happens at the beginning, if we have V in at 0 volt. Here we have VDD, here we have ground. If we start, initially we are somewhere at VDD because our PMOS transistor is conducting, right? This here is closed, so we are at the inner node, VB is fully on VDD. That is true until we reach some VTH, some threshold voltage. Then the PMOS transistor here starts forming a channel. It gets conducting. The NMOS transistor, starts to close the channel. This one starts conducting, the NMOS. So we go towards ground. Since we have an analog circuit at the end, this is not like we go down to 0, but it is some smooth operation. So we have some transition from VDD to ground, and at some point where we have actually correspond to the threshold voltage of to correspond to the threshold voltage of the NMOS, then we are in saturation with the NMOS, the PMOS closes, and we are at 0, right? Okay, does this make sense to you? So we have effectively here more or less than VDD, that's the maximum we can reach, okay? Somehow reasonable? So we started VDD here at the input and slowly increase VDD in this direction. And look what happens to the output. If we increase this, at some point, the NMOS transistor starts conducting. So the inner node is no longer on VDD, but these are two resistors more or less, right? And the more we go into direction of VDD, the lower the resistance of the lower transistors and the higher the resistance of the upper transistor, right? Somewhat, where do I lose you? Okay, because if you can tell me where actually the problem is, where you do not see that something like this should happen, then I can try to explain. No? Yeah. At the moment, this is not about a stable state. It's just the inverter the trajectory, how it looks at the output. I just asked if this here is so far clear that should happen. This here is VB, so I just called the output here VB because that's this node. And this here is just the input, and we virtually take effectively the input, so the node A here. So we can also call this VA. No, I leave it at the moment Vin, because I'm only at an inverter. So I go up with Vin from 0 to VDD. At the beginning, the PMOS is conducting, the NMOS is closed, it's not conducting, until we reach some threshold. Then the PMOS starts to close, the NMOS starts to conduct. So our inner voltage goes down, because it's just a voltage divider then. We have a resistor here, we have a resistor here. The higher the voltage at the input, the higher the resistance of this transistor, the lower the resistance of this transistor. So the voltage at this point decreases. That's what we have in this part. And at some point, this transistor here closes, is fully conducting. This one here is fully non-conducting, there's no channel anymore. So we are at the output at ground. Makes sense? Yeah.
What's that value?
That here is only VTHP. So the threshold voltage of the PMOS transistor should this be something like this. But this somehow makes sense. So can you repeat? I did not hear.
So at the end state, rather than going down to the...
It goes down from VDD to 0, the output. So here's actually the output. The output, this one here, goes from VDD at the beginning at 0 volt to 0 at VDD. That's just what an inverter is. If the input voltage is, so logically this here is 1, this here is 0, this here is 0, this here is 1. If the input is 0, then the output is logically 1. If the input is 1, the output is logically 0. That's, from a logic perspective, we virtually have this as a rectangle sometimes, but in reality, in a physical world, the trajectory would look like this, okay? Good. In a second step now, what I draw is, I draw now VA, so this transistor here, and I put Vin here. So let's call this Vin dash. And we have here actually now the same. So this here is now VA. This here is Vin dash. So we start drawing now here, because we effectively rotated. We start drawing here. We start input voltage is at 1. You can just cheat and look what happens. Well, the output voltage should stay here until the input voltage reaches this VTHP. right? Then the output voltage should go down and end up here. It's exactly the same curve, just flipped. This is actually VA over Vin. Huh? Just that I draw now Vin at this, Vin dash, and VA in this direction. Huh? So it's exactly the same. Okay? Good. Now we look into what happens if we enter some point in our SRAM cell. Yeah? So we actually wanted to have this SRAM cell. So now our input for the cell B, for this part here, just mark it maybe. So this one here, yeah, there the input is Vin, right? This one here, there the input is Vin dash. Vin dash is VB. Vin is VA, right? Okay? Does it make sense? Huh? Okay? Good. Now, what happens if we pick a random point in for our voltage of A and B? Huh? We now say we pick one random point. Where should I go? Say stop. Yeah, so we are here. Yeah, that's our starting point. For where am I? I am on the axis of VA. Yeah? So if we have a certain VA at that point, this is the starting point we decided to have. Huh? Now, if this is the value of VA, it's the input of the green line, right? So we have to select here, we would translate this value to some value of VB. Huh? So this gives us this value of VB, right? So I just make something that of course in reality runs on in an analog world, yeah. But we just make a digital simulation of that, yeah. So this here is our start point. This here is effectively step 1. We calculate our VB for that input. Yeah? If we have a specific VB, then our step 2 is we go to the blue line and we have here, we call this step 2. Huh? We have the new value of VA. Why? With this value of the VB, we drive our output node to a specific value. This output node drives the other one to a specific value, and the thing converges into this point. Makes sense? So if you slightly go away from this middle point here, at some point here, you immediately go into that point. Yeah? Okay? That is what we call a stable state. Yeah? It falls into this point. If I just move it a little bit to the left or to the upper or whatsoever, it still goes back to that point. Yeah? Is this somewhat understandable? Yeah. This one is VA, this one is VB. Yeah? We started with VA, let me see, yeah. Then we drive the VB, which is the green line. VB is between B and ground. This one here, left side. This is ground, yes. Okay. So I just selected here, this one is for VB. We said this here is the input. Yeah, we have here the input, we have here VB. Then we flipped it. We made a second graph where this here is Vin and this here is VA.
Okay.
Yeah, that's the blue line.
Okay.
So both is included in one graph.
Right?
Yeah.
That's VA. Oh, okay.
Yeah?
That's okay.
Okay, that was hard readable, yes. Should improve my writing. Better? Yeah? So, the green one, so, is it clear that we should converge into that point? So we flip the axis, have then a green line for the for the green transistor, the green inverter, the blue line for the blue inverter. The inputs are connected, so Vin is VA. The green Vin is the VA. The VB is the Vn dash. I can also maybe, to make it more visible, we can draw this once like we have this here is our transistor with output node VB and Vin. And we had the second transistor in the other direction effectively with at the output VA and Vin. And then what I did was actually I connected them. So VB becomes Vin dash, I call it here, and VA becomes Vn, right? Okay? And this circuit is the same as this one. Okay? So far? Okay? Yeah? Good. So we converge into that direction. When do we converge here? Can we also let's draw it like this. Yeah. Can we also converge into that point? Can we at some, if with some initialization, so we just randomly select this point. Yeah? You just randomly select it, right? So I could do the same somewhere here, somewhere here. Can I also find a point where I would not converge here, but here? Yeah, under which situation? Well, how did we do the processing? We started somewhere and selected a point on a green line. So I do the same here. Yeah. Then the value of VA is this one. The value of VB becomes that one. The value of VA becomes that one. The value of VB becomes that one. Value of VA is here. We are in that point, right? Because they are cross-coupled. Yeah? Right? So if this one here, if VB goes up, the input of VA goes up, the output of this inverter goes down, so VA goes down, the input of VB goes further up, goes further down, the output VB goes further up, and so on, and we need to go into one of the stable states, right? So, also this one here is a stable state. If we move it a little bit to the left, to the bottom, whatever, we will immediately go back up here, okay? So we have two stable states. What about this one here? They're equal. So what happens if we, by chance, select this point? We stay effectively in this point, right? So nothing happens. It is also stable for the moment, okay? So as long as nothing changed in the circuit, we have found a point. We have somehow reached this point. However this is possible, yeah, maybe during the power on of the device, we somehow reach in this point by chance, and our cell hangs in the state. A state we actually don't want because it means that we have permanent current flowing from VDD to ground, because both transistors are conducting here. So what happens if we have a very small variation on this voltage? We shift. So let's say, maybe I should use yet another color, if I have one. Yes, I have a red. So let us assume we shift slightly to the, from that point, slightly to the left, to the right. What would happen? We would need to take, at that point, the other value, right? That would cause that we converge here, right? If we slightly move out to that point, we would immediately go up. So any tiny noise fluctuation that we always have on our circuit would move us out of this metastable point. This is called the metastable point, because as long as nothing changes and we are perfectly in this point, we are stable. But any small shift out of the stable state moves us into one of this metastable state, moves us in one of the stable states. Huh? That's called the metastable state. Was this somehow understandable? Huh? So this is what, when I say we have a stable state, two stable states, one metastable state, we have the two stable states, which is 0, 1 and 1, 0. Huh? And we have one metastable state where both are somewhere in the middle. Huh? It's usually due to the dimensioning of the transistors, not perfectly VDD, not perfectly VDD half, but somewhere around that. Okay? I just take a quick picture, then I can later upload it to the Moodle course, to the exact course. Good. Okay. Then I remove this a bit. So, then let's go back to the recap part, because I think that we should not consider recap. So we had then said that our SRAM only makes sense if we have larger circuits. So if we have not only one memory cell, but a lot of memory cells. Why? So why do we not use just this single cell here instead of some later lattice flip-flops? Yeah, it's actually always a good guess to say it's cheaper. So, yes, but why? Yeah, but that's already, a flip-flop already is larger than this circuit, yeah? And now if we would say we have just a single bit that we need to store, this here is still smaller. Huh? So why should I use a flip-flop if this here is smaller? So I could always go for that, right? So if it would work like this, yes. The problem is this cell is only then effective if you have here small transistors. Huh? If you have here small transistors, you can hardly drive large loads. Huh? So if you try to read this, it tends, without additional circuits, to change the value that is stored in the circuit. Huh? So if you need to somehow, you don't know what the inner state is. Huh? So you need to somehow preload bitline bar to the same value to get to have a chance that they are at the end different. Huh? To see that there is a difference. Okay? So now if you preload bitline to a specific value, enabling the switch would also impact here the value of A. Huh? And if this impact is too large, then what we had drawn before, these lines say us, if we go over the metastable state for a tiny little nanosecond, picosecond, whatsoever, immediately this thing will flip. Huh? Already if they are not switched precisely at the same time, that would be sufficient. Huh? And we would see just the value from here and not what we had stored internally. Huh? So that means if we just use this cell, we would at the end up in something most likely random. Huh? Because we cannot predict, or in the value which we have here. Huh? So that means we need some additional circuitry that allows us to see the impact of this inner node on the much larger capacitance of this wire here, or on this wire, on both at the end. What is used there is usually a sense amplifier. Yeah? So sense amplifier is built to sense the difference between two wires, that are these two, and to amplify it to VDD ground. That's an analog circuit. Looks pretty much as an SRAM cell, just with different sizing. Good. So we need one sense amplifier on top, another couple of transistors. Then usually we have synchronous circuits. So we want to have a register in between whatever happens here and the outside world. So we need a flip-flop. Now we are already on a level where just a single cell doesn't make sense anymore. Yeah? So what do? We arrange them in an array. Yeah? So if we arrange them in an array, that looks as we had it yesterday here. Yeah? Looks like this. We have still our bit lines, bit line bar. Yeah? Here's the actual SRAM cell with the 6 transistors. And then we have at the end of each bit line bar, it's called chain, yeah? We have one sense amplifier. Now reading out many cells would be slow. We want to have this in parallel. So we make another dimension where we can read parallel. Usually something like we have in that range our word width. Let's say your computer is most likely a 64-bit system. If it's a 64-bit system, then most likely the SRAM in there has a word width of 64-bit. So it can fully parallel read out 64-bit and put them somewhere else where I want to process them. Yeah? That is why we have these in parallel. Yeah? If you have a 32-bit system, then your SRAM is most likely 32-bit wide. Yeah? So the word line enables which word we want to read. The bit lines always go to this sense amplifier and a subsequent register. Now, since we have this structure, we also need some control, because you need to be able to tell this circuitry here, I want to read data, number, whatsoever. This might be encoded in a binary form. Binary form would not directly select a specific word line, so you need some form of decoding. So, if we want to build an SRAM array, we need not only the SRAM cells, which are themselves tiny, but we need on top some sense amplifier, we need a register, we need a control logic. And all of this adds to the area. And for that reason, it only makes sense to implement an SRAM if this array here is large enough. So if you have a few 10, a few 100 bits to store, you would not use an SRAM. It just becomes too large. Consumes a lot of area, hinders you to place and route something where the SRAM is, and so on and so forth. So then you would rather use some flip-flops for that. If you have a large memory, then you spend this overhead, because this overhead is shared among all the cells. And the relative overhead compared to the memory size gets small, so you can use the SRAM as a fast, effective memory. Good. That's approximately where I ended yesterday. And then we had the question, why do we need something else? And there was already the response, well, maybe area, maybe timing. And that's indeed the case. So I skipped this here. So we have, as a next memory version, let's say, we have DRAM and ROM, which are completely different things. I just have them as next step. I already said the SRAM is usually on your chip, on your in your cache. Because it's fast, because it's very stable. But it is the smallest version we have. The smallest what we have is effectively the DRAM, or the highest integrated. Where do you have DRAM in your computer? No idea? So if today you need large memory, so SRAM usually is small. So it's on the chip, it's relatively small. If you need large memory, for instance, DDR5, what you buy is some dedicated memory chip, that's DRAM. So these are DRAM chips. There is a little bit of logic on top that controls the DRAM, but the rest is only memory. Good. Let's first have a look into how this works, and then we can also discuss why it's not integrated in the chip. So DRAM looks as follows. we have one transistor that is effectively a switch. So this here is virtually only a switch that we can switch on and off, and we have a capacitor. So how would the process of writing work? Let us assume we want to write a 1 to our memory. We apply here a 1. Electrons, we close the switch. Electrons will move towards VDD. So we have here some positive loads, right? Then we open the switch and they stay there, right? So we have a capacity, we load there. So the charges, for the moment, in an ideal world, cannot go anywhere. They are stored. Makes sense? We captured them somewhere. If we want to read, we apply here VDD half. So we put here VDD half so that we have somewhere in the middle. We open the switch or make this here conducting. Some of the electrons go here, which causes, if we look into some time diagram where we have, let's say, VDD here and ground here, then we start with the BL being somewhere in the middle. If we close the switch, in that case, well, our VDD will go a tiny little bit up, and then most likely down again. So what we need again is, at that position, we need a sense amplifier that senses this tiny peak, and then amplifies it to the full VDD ground level. So far, makes sense? Same, by the way, if we want to store a 0. If you want to store a 0, effectively, we discharge this thing, or we put this here to 0. So we have here effectively the, let's say, ground level. We remove here the this connection, and our reading would look like we have a tiny thing in direction of ground. And then, of course, you have the sense amplifier here at the end of the bit line. Now, if you add the sense amplifier, then maybe I take here this one. Then we would here have, I just write SA for sense amplifier. This one here would be amplified somewhere VDD. This here would be amplified somewhere to ground. So this is just, all right, sense amp, sense amplifier. So what does this mean? If we, probably I just to better draw it, I just remove this for the moment again. If we are up here, so we go back to that situation. We have charges, positive charges here on the capacity. We close here the switch, here the connection. So we said, okay, some electrons go here, recombine with the positive charges. We have a tiny peak. Now we have here a sense amplifier. So at that point, here, some of these are removed. They just disappear because it modifies all the voltage here. So they start recombining. Now what happens is that the sense amplifier amplifies that wire up to VDD again, because we have this tiny peak. So sense amp causes here VDD again. This VDD applied by the sense amplifier causes, since the switch is still closed, that again we store here the value of 1, right? So we first unload this capacity a little bit, which causes some voltage fluctuation here on this bit line. This voltage fluctuation is detected by a sense amplifier, which in an analog way just amplifies back to VDD. this amplification for VDD causes a rewrite of this capacity so that the capacity goes back up to VDD. Yeah? Then our write process is ended. We can remove here the switch and we store still the same value. Okay? In that way, we ensure that the reading process does not destroy the stored value. Somewhat reasonable. So, if we close the switch, the positive loads here recombine with the electrons from here, causing a voltage fluctuation here, causing a decrease of the voltage here. If we would not amplify something, these few charges here compared to the large load of this here would just disappear. Huh? So we are somewhere at VDD half, and yeah, because this here is so if I see this, I see here a very large capacitance, much larger than this one, right? If I put, let's say, here only 2 loads, and here I have 4, and I open a switch, then some of this positive loads should go here, right? So decreasing the voltage here, and if this is much larger than that one, we will end up somewhere approximately where we were here. Not really distinguishable, because there are only so few loads on this tiny capacity. Yeah? If it's on a tiny capacity, the cell is not small. So there are only so few loads on that this one will just overwrite it. Huh? So what we need is that we also refresh this value. And refreshing this value happens because we have a driver implemented as a sense amplifier that amplifies here back to VDD. So virtually we put here now a lot of positive loads by the sense amplifier. Maybe I should write them in orange. So they are caused by the sense amplifier. And now again here some of this or the same value as this overall thing should come up, right? Okay. So this is what happens in a read process. Now, so far, okay? Good. So now what we need to ensure is that, well, I just can remove that. And we go back to the step where we had stored some value here. Yeah? So we have stored some charges here on top of this. Yeah? Disabled the switch, and we have the charges here. As that in an ideal world, we store this value forever. What happens in reality? So in theory, if I open the switch, I have here charges, they stay there. Nothing will happen. But we are not in an ideal world. Yeah? So we are in a physical world where all physical rules apply, and unfortunately that's not perfect from an engineering perspective. So what would happen in a real world? There's some charges are lost, right? So we have some leakage current that causes that some of this are cancelled over time, right? So the voltage on this capacitor here decreases over time. Huh? That's not what we want to have, right? What can we do against it? Recharge. How do we recharge? We read the cell. Huh? So we need to have for this DRAM is very small, but to make it running, we need to have, first of all, we need a capacity. This capacitance is hard to integrate with CMOS processes. That is why you do not integrate it on the chip. And the second problem we have here is that we need this recharging of the cells, which means every now and then we need to read the cells. There are intervals, how frequently this is read, that depends on the technology and so on, so nothing we need to learn here. If you do it in a clever way, you can combine this with the regular reading process. So if some parts are already read, you do not have to refresh them. you can just leave them because you know, okay, I just read them, and reading them means refreshing. So, yes. So this is why they built this or that the hard to integrate part is why they built this usually in a dedicated chips. There is some effort going on to bring these chips, these DRAM chips, close to the actual computation unit. In sense of directly attaching this, this is a, nowadays, I would still say novel technology, which is called chiplet. So you build with one technology the one chip, the other with another technology the other chip, and then glue it more or less together. Why do they want to do this? Because this is a little bit slower than SRAM, but you can have massively more memory on the same area for the same cost. And if you now think of new applications for AI, then what they need is a lot of memory because all this AI stuff is incredibly memory hungry. You have to load a lot of data, you have to construct a lot of data, and so on and so forth. So, and for that purpose, you want to have this as close as possible to your compute unit so that you can immediately access this memory without loading over some external bus, long external wires, I/O buffers, and so on, data from somewhere else into some internal cache, then into some closer cache, and so on, and then finally process it. So that's the idea why they try to bring it closer to the chip, but I would say we are not yet there. Good. Okay, questions to that? No? Good. Then the next kind of memory is ROM. You can build this as in two variants, NAND or NOR-based ROM. We have here NOR-based ROM, which is the most common one. That is effectively, from an engineering perspective, relatively simple. What you have is, as before, we have a word line to select specific cells. We have bit lines, which give us, at the end, the output. So if you want to read a specific word in our memory, we enable the word line, the corresponding one, and we have at the output the bit line. Again, here on top, we have some form of a sense amplifier and so on. So how do we physically implement this? Well, we have kind of CMOS-looking structure with, I have here things that are connected, transistors are connected, NMOS transistors are not connected. And I have a PLS, which is independently controlled from the NMOS. So what is PLS? That is actually some pre-charge transistors. So from a general idea, let's go for the, let's say, for the very right line. Yes? It's a pre-charge signal. I cannot really say what the L stands for, but pre-charge maybe logic signal. I don't know. But it's for pre-charging. So the purpose of this is, now, if we see a wire here, we can understand a wire as a capacitor, right? So I just do this for the very right here. We have a capacitor here. Now we enable this PLS signal. So PLS goes high. If PLS goes high, this capacitor here is charged to VDD, right? So, okay. So we have here VDD if PLS equals 1. So if PLS goes high, we have here, sorry, goes 0 should be. 1 second, should be 0. Then we set PLS to 1. meaning we disconnect here from VDD. So this here is PLS equals 1, right? Makes sense? Good. So, similar to what we have with the DRAM, right? We have a capacitor which is pre-charged. We do not have yet the information what is stored in the cells. How do we get this? We now enable the relevant word line. So let's say we enable, which one? Let's say we enable word line, this one here. Yeah? So if the word line here is set to 1, in that case, we have a connect from here to ground. Right? So if we have here a connect to ground, we would have here electrons flowing in. Sorry, that's the wrong path. I should be precise here. From here. Right? So we remove whatever charges are here. Because now word line is at 1. Okay? So this value is logically now at 0. Right? Makes sense? Because we have discharged this capacitor. Now let's go maybe for for this word line here. Yeah? If we do the same thing, we pre-charge this here to VDD, which is 1, enable the word line, then here, this here is unconnected, right? There's no connection here to ground at that point. For VDD, let me quickly think for 1 second. So if you think about an inverter, right? If the input is 0, so just if you think about an inverter, that's the easiest way, I think, to imagine this. If here is a 0, then here we have a 1. So if this here is 0, this one here is conducting. So if we want to have this here conducting, the PLS should be a 0. Right? Okay? I had it wrong before. That's because it's a little bit unintuitive because it's this inverting character. Good. But here now, in this case, for the other word line here, we have no connection. So if we pre-charge here to VDD, open the switch so that only the capacitance here holds some charges, and then activate the word line, nothing happens. If we read here, there are charges on this capacitor given built by the wire. So we would switch to a 1, right? So in that sense, we can interpret what we have stored here, right? So we have here a disconnection, which is a 1, no connection, which is a 1, a connection, which is a 0, here 0, here a 0, this is a 1, 1, 1, and these are all at the end zeros because we always have a connection, right? Okay? Probably one thing to add that a question that might pop up in your minds. If we have here no connections, why do I draw a transistor here? So we could just remove it. And indeed, that's true. The reason why I draw it is that in practice, usually it's built. So you build the transistors, you just do not the connect, because in that way you have a more regular structure which is easier to build. That's the only reason why we have the transistors here at all. Okay? Yes? Why?
When PLS is 1, right? Why 1?
So if PLS is 0, then we are conducting here. It becomes, so the process, maybe I should write this. So we have the PLS, which is initially at 0. So if this is at 0, I talk about this here as BL. Then BL is at 1. So we have here 0, 1. And here also 0, 1. Then we have the word line, which I had, maybe I take the orange color. we have the word line. This is until here 0. Huh? Now we switch here to 1. Huh? So we disconnect here. Then BL will, well, it will slightly unload because of some currents that will, some leakage currents, but it more or less stays at VDD. So it just goes a little bit below. And now we enable the word line, right? And this word line now connects to this point here via this transistor X. So if we connect via this transistor X, then this will immediately discharge this node, right? Because we have connection to ground. So this is, 1 second, for let's say, for X. Now consider this for, let's say, node here, this here, Y. Yeah? We call this maybe word line Y. Yeah? So if we enable here instead of, so maybe I make another cycle to make this more readable. So this one here can go back and we are done. But we have now this word line Y, which goes up somewhere here. Yeah? Again, we have the bit line. So that's the same actually. I just write here X and here Y. So the bit line is still the same because we selected the same column. So our bit line at that point is recharged to VDD, right? Because PLS goes low. And if it's disconnected here, it again starts slightly discharging. And at the point we connected here, there is no connect. So it just continues virtually. But now, during this reading process, we use a sense amplifier, which then causes effectively that we amplify this back to VDD and can read out the value. Yes?
Why is the right line of
So, to be correct, this would be, so if I zoom in into this, for instance, then correctly it would be, we are at the beginning, or let's better zoom in maybe in, yeah, I stay here. So we are at a state VDD, then we have a capacitance behavior, right? So that will somehow decrease, something like that. Then we are at that point, and that will also not be something like this, but it will most likely be such a curve.
I see.
So in reality, of course, this is not a rect angel. Never. So rect angels do not happen in analog.
But, so this point here starts to discharge.
Yes.
Right?
Yes.
Then only when the red line 1 looks something like not as a right angle. Can
Yes.
I say that both of these 2 points are?
Yes, both these points are exactly the same. So this is actually is this part here. This part here is the same as this part, and it's the same as this part. This here only happens here.
Am I right with 8 lines and they are not one as a...
Yes, I use only one as an example because otherwise I have to write too much.
Yeah, okay. Yeah. Understand.
Okay. How the word line is controlled, actually? Yeah, you have for all of the things that what I mean before was you have a control logic on top. Yeah? So your overall memory is actually you have like this, yeah? Instead of the SRAM cells here, now we have only one bit line and we have only one transistor to discharge, but overall it looks pretty much the same, right? You have such a structure, and at the end you need here some sense amplifier, some register, and you need to decide which words are used, you need some control logic. What normally happens is you tell from your software program, I want to read a specific memory address into my register of the processor, right? Then I access this. I need some decoding here to translate a binary encoded address into some one hot encoded, so one word line is enabled. And that's it. Okay. Shall we have a 15-minute break? Yes? Good. Then we continue in 10:40. With something which is just in the stable state. Maybe we can discuss later because otherwise yeah. Okay, let's continue. So I think we took the time to clarify most of the questions that popped up. So what is maybe an important thing I should add is now maybe in the meantime also clear to all. The big drawback of ROM is it is, at least in the version I've drawn here, it is design time programmable only. Meaning, as a designer, I have to decide what is in the memory, and then as long as the chip exists, it's there. There are some forms of ROM, so electronic programmable ROM, EEPROM, light programmable ROM, something like this, where you can a limited time of programmable programs, reprogrammings do. There are also one-time programmable ROMs where you implement here this connection with kind of fuses. And if you want to program a specific word into it, then you blow a fuse. And then for the rest of the lifetime of the circuit, this becomes a 0. And the rest, where you don't blow the fuse, that's a 1. Or other way around, sorry. Where you blow the fuse, it's a 1, and where you don't blow the fuse, it's a 0. So, there are variants of this, but at the end you have no or only a very limited number of reprogramming options. Any idea where such a kind of memory could be useful? Yeah. So the comment was bias. Effectively in the boot sequence of the computer, the initial steps you can implement, or is a typical place that is implemented with ROM. Because you have something which is sufficiently complex that you need some memory. You cannot just implement this in pure logic, but it should stay constant over the complete lifetime of the chip. That is where it's used. And it's usually quite small because, well, we have only one transistor, plus for the complete row we have this, this PLS, plus of course some sense amplifier and some register. But at the end, it's even smaller than what we have with the DRAM, right? Okay, that was it with what we classically think of if we say we have some memory. What also belongs to the memory elements, obviously, are latches and flip-flops. Did you do something on that? Probably. So let's quickly look into this. Somehow a known structure. So we start with latches, not with flip-flops, because flip-flops are based on latches. We have two classical variants. New circuits also operate with other kinds of latches. But we stay with this one. Here for the course, we just take these two, RS latch, and there are two variants for this RS latch. The one is this NOR-based. The other one is this NAND-based. The NAND-based is widely used. You may do some computations for the NOR-based, just for some exercises, but at the end, this is what you go for, and that's also what we discuss in the course. So, what do we have? We have, coming from the NOR-based, a set and a reset signal, and if we have the set signal put to 1, we want to have Q at 1. If we have the reset signal at 1, we want to have Q at 0. And Q bar should be, please, the inverted signal. Similar for the NAND-based, we want to have at the output here a 1 if our set signal is at 1, a 0 if our reset signal is at 1. But you need to take a little bit of care because here the input is also inverted. So there's effectively, this is a not set signal and this is a not reset signal. So that's more or less the functionality. Now, let's look a little bit into the states that we have, what happens here, because that shows us why this, these latches are at the end not what we want to have for digital circuits. Or only with, let's say, taken with care. So, first I want to explain what I have actually written on the slide, because otherwise I know that causes confusion. So, in an analog world, we have, at each point in time, we have one value. But to think about this flip-flop, the switching behavior, we need effectively a time dependence. This is why I say, okay, I have a current set signal. I have a current reset signal that's in time point t. So this index t just means that's the current thing. We have some outcome for the current time step, which is qt and qt bar. So that are just this is what we have in our flip-flop now. Our flip-flop here has a feedback. So the output of this NAND gate here depends not only on our current R, but it also depends on what we previously had at the value of Q, right? So in order to build a logic table, we also need to consider what was the value at the time point before we started switching. So what was stored before? And that is what I mark here as Qt minus 1 and Q bar t minus 1. Yeah, we will see. So what I further have to have not 2 to the power 4 different inputs, I reduce this by saying Q or Q bar can take a value A or B. And A or B are just placeholders for 0, 1. So, nevertheless, we can start with, with the maybe set and reset state. That's the simplest one. So, the set state says we have this here as 1, this one here as 0. We know that's a NAND gate. A NAND gate at the output, if one input is 0, should be 1. So then the input here is a 1, and we have here 1. So the output is a 0, right? Should be. Why is this different from the set state here? Or effectively, why is this the reset state? Well, we have here set inverse, reset inverse. So if we have the set inverse at 1 and the reset inverse in 0, then obviously set is 0, reset is 1, and that's a reset state. So, good. Is here, you're right. No impact, whatever the Q and QT minus 1 is. So that's why I have here A and B, because A can be 0, 1, this can be 0, 1. I can have arbitrary combinations of this. Always the output is here 1, 0. I don't have a problem. No? Good. Then we can go for the set state. Same thing the other way around. We have here a 0. We have here a 1. So the output here is driven to 1. If this is a 1, this is a 1, 1, 1 gives here a 0. Right? I did not have to consider anything from the internal state. Perfectly fine. Okay, so that's this state here. 0, 1. Here, 0, 1 gives a Z with Qt is 1 and Qt bar is 0. So these two lines, straightforward. The next one is, so maybe I now put this here away. And we put here we put here 1 and 1. Can happen. Now if there's 1, 1, what is the output of this here? Y? Yes, I said I put set and reset too high. So for simplicity, let us assume we have here a value A, can be 0 or 1, and we have here a value A bar. So this here is 0, 1, then this here is 1, 0. Yeah? It's inverted, because we have set and reset. This is now the value at the time point t minus 1. That is what we stored before, or reset before. And then the second signal occurs. Now, if the input here is a 1, the output is a 0, right? So if A bar is applied here, the output is A, right? And the other way around, if A is applied here, if this is a 0, the output will be a 1. If this is a 1, the output will be a 0. So this is A bar, right? So this is what I have here in the first line, and we call this store. The value does not change. Okay, now these are the intended cases. That is where the latch is built for. Now we have another state. Namely, it does not make logical sense to have this, but it can happen just because of runtime differences in our circuit. We have a case where S, and R are both 0. Okay? What happens? Well, if one of the inputs is 0, output should be 1, right? Because it's an AND gate. So we have a 1 here and a 1 here. No problem so far. It is logically, it doesn't make sense because now Q bar is the same as Q, right? But besides of this, well, who cares? Good. Now I go from this into a store. So I now transit from 0, 0 directly into 1, 1. What happens? So we have here 0, 0, which is, I call forbidden state. Here, go directly to 1, 1. What happens? Yes, why? Why? Because it's there, right? So, if we had 0, 0 here, we had here 1, 1, right? So if we have here 1, 1, then we should here at the input also have 1, 1. Yeah? So that's our previous state. Now if we have here 1, 1, and here 1, 1, the output for 1, 1 should be a 0. The output for 1, 1 should be a 0, right? So this here becomes a 0. If the input of the NAND gate is a 0, output should be a 1, right? So that causes now in the next, in our, let's say, in-mind simulation, causes that the output here goes back to 1. So the input goes back to 1. So the output goes back to 0. And we oscillate. Yeah? In practice, most likely this will not oscillate forever, to be honest. Why? Because these two NAND gates have different driver strengths. So it will hang around in this, around this metastable state, consume a lot of power, and then go into one of the two stable states which we cannot predict beforehand. But at least from a theoretical perspective, it oscillates. Yeah? That's why I write oscillating. So this is a case where we effectively drive our circuit for a longer time in a metastable state. And, well, if we are unlucky, we destroy the circuit because we burn a lot of power, we make it hot, and it's destroyed. Yeah? Not so nice. Yeah? Benefit of these latches is it's very small, yeah? And you do not depend on the clock, so you can do something clock-independent asynchronous. Most of the time in digital circuits, we want to be synchronous for good reason, because we can then do timing simulation, we can predict how a circuit behaves, we can be sure that a circuit at the end is functioning, yeah? And we can break down our whole circuit design into clock cycles and not simulating all at the same time. Yeah? Which makes it, from a tooling perspective, very interesting to have a synchronous circuit, because then we can do all the tools or use all the tools we have today. Yeah? And only with them we can design really complex circuits. So, now we have this behavior. What do? Well, we try to make it synchronous. We try to remove this, let's say, ugly effect. And the next development for that was in the direction of a so-called JK flip-flop, I would say. Nowadays, there are other flip-flops which work with multiplexer structures, which are smaller, but from the concept, it's more or less the same, so I only go for this JK flip-flop. So, this is not yet the JK flip-flop. This is actually JK latch, to be precise. What does this change? So, effectively, we have the same structure as before. We have this RS latch. Yeah? So RS latch was, we have two NAND gates, cross-coupled, and here the connect. Yeah? So, and on top of this, now there is an additional feedback from Q to R bar and from Q bar to S bar. What does this help? So we neglect this clock edge thing for the moment. So assume we have this A bar case for the internal state. So they're just, the one is A, the other one is A bar. And we apply for both input 0. So J and K is 0. We neglect this here. Then the output here is 1. So S bar and R bar is 1. And if you look it up at the previous slide, if S bar and R bar is 1, we are in the store state. So that's just as before. If we put J to 0, K to 1, then the output here should be 1, right? So this here is a 1. If this here is also 1, the output should be a 0. This here is a 0. Say correctly. So we other way around. Yeah? So this is inverted. So this here is, I need to write it down. Sorry, I was for myself too quick. So if this here is a where are we? J is a 0. This here is a 1. If we are in that line, then this here should become a 1. If this here is a 1, the output here, or if this here is a 1, this here is, I go back to the slide before, then we can just cheat. So we have effectively this case, set as a 1, right? Then we are in the reset state. So now if we have the other case, we have here 1, here 0, then we have this is set to 1. If we just look it up before, if reset bar is a 1, this is the case where we have the set state. And then we have this last thing, which was before called forbidden state, where we have at both inputs a 1. Now if both inputs are 1 here, in that case, then the inputs are Q bar and Q, right? Because we have this feedback. So effectively, if Q is a 0, before. Then we have at the output a 1. If Q is a 1 before, we have at the output a 0, right? So this here becomes Q bar, and here we have effectively Q, right? And this causes that now the output toggles. Huh? So we have still something that oscillates, right? So why should this be better? Well, we can now make the time where we can switch this flip-flop, at least virtually, very small, very short. No? This idea at least existed. If we make this very short enough, then this will flip, the bit will change, but it changes only one time, so it toggles the bit, and then we are done. If we, and then if the feedback arrives, then already this high signal is gone, and we are safe so far. Okay, so if you have this short enough, it should be okay, right? So from a theoretical perspective, we could build here something that generates a glitch. Could look like this. And if you build such a glitch generator that is designed so that here the time is very short for switching, then this here is disabled before the signal feeds back, and you only toggle. You don't oscillate. By the way, what will not happen here is this behavior that you go into the metastable state. That does not longer happen. Why not? Because you have here, you cannot, due to this feedback, go back to the store state. Or if you go to the store state, you still have at the input 0, 1 because of the Q feedback. So this metastability issue does not exist. But you still have this oscillation state, and that you can try to control with the length of the pulse here at this edge generator. Now, in practice, we do something a bit different. Namely, something called JK master-slave flip-flop. So I do this, I have not on the slides, but I can will quickly show you the idea on this visualizer. So probably we keep for a moment this the slide, and I draw first some RS latch. So we have S bar, R bar, Q, and Q bar. It's just an NAND-based RS latch. Then we can extend this to this JK flip-flop or JK latch. We do not fully do this, but at least I put here at the input 2 NAND gates for the moment. One we call J, the other one has the input K. Then I put here the clock signal. So now the thing should toggle if JK has some values and if the clock is high, right? Now the output of this we send to a second flip-flop. So we have a second latch here, S bar, R bar, and again Q bar, and again I form something like this JK flip-flop. So now I have two such structures, and the Q bar here we feed back to the very first input. The Q we feed back to the other input, and here in the middle we put another time the clock, but this time we put it inverted. Okay. What happens now? We have two parts here. First latch, second latch. The first latch here can also be seen as level triggered flip-flop. So as long as our clock is, are there any questions? So as long as the clock here is at 1, the output here is controlled by j, k, and the internal state. Yeah? Internal state inside of the state that we see here. If the clock is at 0, the output here is 1. And if you remember back, output at 1 means this here is in the store state. So nothing changes. Right? So only when the clock level is high, only in the high part of the period, the first flip-flop here can do something. Then we have here an inversion of the clock. So what happens at that point? If the clock is high, the output here, so if this clock is high, this here is low, is 0. If this is 0, the output here is 1. So in the high phase, the second part here does not operate. Right? So the second latch only operates in the time where the clock is 0. The first part only operates in the time the clock is 1. Correct? Okay? Not okay? Yeah? Good. Okay. Now let's see what happens if we propagate, if we are in time phase where we operate for the first half, and we have j and k, let's say, both at 1. No, 1 and 0. Yeah? So we operate, so if this is 1 and 0, the output will be from this here will be a 1. And then if you look it up before, its reset bar is 1. And this will cause that this internal state here goes into a reset. Yeah. No, R bar is 1, and then the internal state is set, right? So we are in a set state here. Q should be 1. And the whole thing is effectively, is in the fixed state. Now we have Q1 and Q bar 0 in the next state. So with the falling clock edge, the value is propagated here, processed at that point. So we have an inversion, right? So if we had before Q at 1, doesn't really matter, then here S bar is at 0, right? So we are in a Z state, Q is set to 1. Then the feedback is enabled, and our effectively J and K is propagated from input to output. Right? That's the first state, case we have. The second case we have is that J and K are both set to, or the other way around, then we have also set an output, and if you compute this, you see it's then the reset state. The third is you have both at 0, then whatever you have here is stored because it's just inverted, right? And if this here is stored, the output does also not change, right? And the last case is that both are 1. If both inputs are 1 and the clock is 1, then what comes back is just Q bar and Q as the input, which is the input here. This is here inverted. In the next clock cycle, applied here, and another time inverted, and we just toggle the output. So, but now this toggle is not dependent on the clock, because when this here toggles, this here is inactive. When this here toggles, this here is inactive. So one propagation delay of the whole thing takes 1 clock cycle, right? So we are perfectly synchronous. Now, what do we have here in terms of, to connect this with what we had previously, in terms of setup and hold time? Because we talked about setup hold times the last days a little bit. And we said, okay, for a flip-flop, setup hold time is critical. So how does what we see here relate to setup time in the first, maybe? Any idea how we, or where we can see here something related to the setup time? So effectively, the way I've drawn this, we depend on the falling clock edge, right? So with the rising clock edge, the first flip-flop is enabled, with the falling clock edge, the second flip-flop is enabled. So we send, finally, we send data out with the falling clock edge, right? What does it have to do with the setup time? With the setup time, this is now related to the falling clock edge because we trigger on the falling clock edge, otherwise we just need an inverter here at the beginning. Now, the propagation of the signals here into this inner node, here. There's a propagation time. Do you agree? So, this is not zero time, this is not a pure digital world, it's an analog world. So we need some propagation time from the input to here. If we switch our clock while here something's propagating, we cannot reliably say what the internal state is, because not everything is settled. So maybe we go back here. So we had here already the case that if you, let's see, go for instance from reset to set, then you have here something depending on the set and on the S and the R bar. So we have, let's say, we want to reset from a set state. Then we put the S bar to 1, the R bar to 0. R bar to 0 has an immediate impact because it changes the output value here. The S bar to 1 has no immediate effect, right? So, because this is 1, but if the internal state here is, I have to try again because I need to concentrate. So, if we have, let's say we are in a state where we have the set. So we have Q at 1 and Q bar at 0. So we have here 1 and here 0. Now if we go into this reset, so we pull this here to 0, this here to 1, then in a time simulation over time, first the Q bar will go to 1, and if this is 1, I try to explain what we have here for problem with this here. If we go here from 0 to 1, then this here goes from 0 to 1. In this first virtual time step, this here remains at 1 because here is 1, 0, right? And 1, 0 should drive to 1. And only then in a third time step where this here is already settled, this here goes to 0 and then we are done, right? Okay? Does the sequence make sense to you? Yes, no, maybe? So what I tried to say is you have in the physical world, you have a timing behavior there, right? And you're only done when you reach the last step, okay? So what happens now if we put at that point here, where we are here, we just reset this here to 1. So instead of having here longer 0, we put this here to 1. Then the output here should be driven back to 0, right? Because we have 1, 1 should give a 0. It should give a 0. Makes sense? Makes no sense? Any idea what I'm talking about? No, maybe, yes. Still alive? Is it clear that this thing here has some timing behavior? Yes, good. So we have a timing behavior here. If we switch off here at the wrong point in time, too early, the output here is not decided yet, right? So what does it have to do with this one here? If we toggle the clock too early, this RS latch did not settle. We are in something undecided, but we remove the input signal. So we violate the setup time. We have too short time to modify this internal node in order to have the correct internal value. Because it takes some time until the signal propagates in. Okay? So this is effectively the reason why we have here some setup time. Huh? Then we have a second part. If the clock edge comes, that effectively sends the data out from the internal node, namely the clock edge which disables this flip-flop, this latch, and enables this latch. Yeah? Then it first takes some time until we propagate out, yeah? Which we call propagation time. Yeah? So we have some delay of the flip-flop added from here, effectively from here to here, which is effectively the propagation delay. Yeah? And then we had some hold time problems, huh? That the signal should be stable after a clock edge. Huh? So what does this relate to? Well, effectively, we have some feedback that must be triggered, right? And only when the propagation back here is completed, only then we can be sure that any signal that comes in does not unintentionally modify what we have here. Yeah? So we have effectively some feedback here, feedback loop, and that corresponds to our hold time. Yeah? So we have the three components that we had before on a more, let's say, virtual level. We have setup time, hold time we talked about. We also talked about clock to queue. Yeah? So clock to queue, hold time, we need to trigger this latching effect. Setup time, we need to propagate the signal in here. Yeah? That is why these things exist. Okay? Nevertheless, if we build the thing like this and respect the setup and hold times, then we do not have these metastability issues here anymore. And we have something that is really clear on the, in that case, falling, in general, rising or falling edge. Huh? So only on this edge, the internal state effectively propagates. Huh? And before, it's just stored internally and not sent out. So we send with the rising edge, we have something synchronous. And during this time where we send, we cannot modify the input because it's just blocked by the clock. Okay. Most of the time, we have we have not such a differential thing, huh? Where we have two inputs, two outputs in a digital circuit. Most of the time, we have D flip-flops or a specific variant, which is toggle flip-flops, which is used, for instance, to count a number of clock cycles or something like this, or toggle input toggles. So that can be easily implemented from or transformed from this JK flip-flop. There are also more efficient implementations, again, with multiplexer structures. Yeah? But if we want to build this from a JK flip-flop, we can just connect J and K to 1. Yeah? Then we have the same as we had on the previous slide. We have this master-slave flip-flop as in this, what I've drawn. The input signal that toggles the flip-flop becomes the clock. And every time the clock arrives, since there are both values at 1, we toggle the internal state, we toggle the output. If we connect J to a data signal, then K to the inverse, then we reduce our possible inputs effectively to 0, 1 and 1, 0, so to set and reset. If D is 1 and the clock arrives, we have a set. If D is 0 and the clock arrives, we have reset. So the internal state becomes set reset, and the output is then at the next rising edge available, or at the next clock edge available. So this is how we can just simply transform what we had on the previous, or on this hand-drawn thing, what we have, or what we can do to implement a standard D flip-flop as you have in each computer 100 times, million times. it's nothing can be implemented like this. As I said, usually today you implement this with a multiplex structure, but I don't want to go into different MOS implementation techniques. Okay, so far okay? Any questions to that? No? Good. Well, maybe I stay quickly here. As you can imagine, of course, or as you see, well, the SRAM cell is very tiny. This one here is way larger. Yeah? If you have two RS latches, that means 2 NAND gates, four NAND gates for the two RS latches. Then we have at the input each 2 NAND gates with now 3 inputs. So another 4 plus 2 inverters. So we have a lot more gates, more area to implement such a flip-flop. Also in more efficient designs. That is, if we want to store a large amount of data, several hundred bits, then we go for SRAM. If we need only a few bits, then we go for these flip-flops. Maybe one tiny bit unrelated question, probably to wake you up. We have here 3 input NAND gates. We have said a 2 input NAND gate looks like this. We have VD ground. So this is a 2 input NAND gate. What do I need to do if I want to implement a 3 input NAND gate? We said this here is a 2 input NAND gate. This here is output. This is A, this is B. Yeah? Yes. So we have 2 inputs, A and B, so it's 2 input. Yeah? But now we want to have 3 inputs. What to do? Okay? And now? Where? An AND gate? So transistor? What transistor? What transistor where? That's actually the question. PMOS? Between? Like this? What would happen? So we apply signal 1 to C. What would happen? Or signal 0 to C? It's better maybe? Yeah, but what would happen? So it's fine to guess, just maybe you can see why it should not be. Huh? What means for us, let's say we have here 1, 0. Huh? And here a 0. That is the same situation as VDD, 0 and 0, right? What would you have if here is a 0? So, yes. So, this is always my personal helper. Huh? If here is a 0, then this here should be shorted, right? So, that would mean if you connect it here, there's a short circuit, right? So, no, that we don't want. What do we want? Well, we want to implement a truth table, right? Now with A, B, C out. I just write maybe first this one here. That is what we have as inputs, as possible inputs. And then we had here already, this should be a 0. This here was before a 1, should now become a 0. No, was also 0 already before. No, wrong, sorry. This is a 1, was already a 1 before, like this. This here is a 1, was already a 1 before. This is a 1, was already a 1 before. This should become a 1, was a 0 before, right? So we need a pull up. This here was before a 1, should stay a 1. This here was before a 1 and should stay a 1. This here was before a 1 and should stay a 1. This was a 0 and should stay a 0, right? So in brackets is actually the NAND gate, 1, 1, 1, 0, 1, 1, 1, 0 with 2 inputs for A and B. And the other one is the actual output that we want to have. Right? So what do we need to add effectively? We need at this point, we need to pull to VDD, right? Because we had here a 0, and now we want to have a 1, right? And then we are more or less done, okay? So, what we finally need is we add here another PMOS, connected to C. Now we have the effect that if here is a 0 and these two are 1, so for that case, we have a short circuit. So, we add another NMOS here, and now we are done. So, if one of the three here is a 0, we pull to 0. Huh? No, if other way around. Sorry. If one of the three is a 1, we disconnect from ground. If one of them is 1, we have to redo. It's already a little bit too much. So, if one of the three inputs becomes a 0, then we connect to VDD here, and we disconnect from ground here. Only if all of them are 0, we connect to ground. We disconnect from ground, and we connect to VDD, right? Yes. So it's nothing else than switches at the end. So in CMOS technology, the resistors are nothing else than switches. Now, what would you do if you want to build a NAND with 4 inputs, 5 inputs, 6 inputs? You do the same again. That works up to a certain extent. At some point, since even if they are on, they have some resistance. At some point, this will no longer work without scaling up massively the transistors and so on and so forth. So you cannot do this in physical designs. In a physical world, you cannot scale this up an arbitrary number of times. But on a logic level, you can just scale it up. Okay, that was a quick excursus. The last thing I want to do is a comparison between the things. So flip-flops we usually use when we are, or flip-flops are the synchronous element we have. Latches asynchronous, SRAM, DRAM, ROM, usually implemented as synchronous design by using additional flip-flops. But you could theoretically also implement them asynchronously. The timing, since we have it usually, since we have it synchronous, for the flip-flops, well predictable. For latches, the difficulty is that you have to consider the complete circuit. It does not break your circuit into clock cycles, so that is okay if you know what you do. Usually you avoid it. If you are on an FPGA and you ever see in your synthesis warning latch, don't know, and you did this unintentionally, you have at the end a runtime problem. That is for certain. Area is from left to right smaller, so latch is larger than SRAM, flip-flop is larger than latch. If we want to build something decentralized, in sense we want to be close to our data, you are directly in the processor core, then you go for flip-flops or maybe latches if you want to have something asynchronous. If you have something large, centralized, like a cache in your computer, then you go for an SRAM. Okay, I think that's enough for today, and we see us tomorrow morning. Sure.
One is, what do you mean by decentralized?